People ask me all the time, how far is Mars? How far is the Moon? How far is Alpha Centauri? And NASA scientists will give you these very precise numbers. They'll tell you Mars is 225 million kilometers away or something like that. The Moon is exactly 400 kilometers. But here's the thing, and I'm not saying NASA is lying to you, I'm not saying that at all, but there's this fundamental problem with how we measure distances in space that NASA kind of has to dance around. They can't tell you the whole truth because the whole truth is much more complicated, much more uncertain, and much more interesting than they usually have time to explain. Let me start with something simple. If I wanted to measure the distance between 2 points in this room, what would I do? I'd get a ruler, right? I'd stretch it out and I'd count the marks. 1 foot, 2 feet, 3 feet. The measurement is direct. I can see the entire distance with my own eyes. But now imagine the 2 points are so far apart that I can't possibly stretch a ruler between them, not even a really, really long one. That's when things get tricky. That's when you have to be clever. And that's where the real story begins. Here's the first clever idea, triangulation. Let's say there's a mountain way off in the distance and I want to know how far away it is. I stand at point A and I look at the mountain. I measure the angle from where I'm standing to the top of that mountain. Then I walk a known distance. Let's say I walk 1 kilometer to point B, and I measure the angle again from that new position. Now I have 2 angles, and I know the distance between my 2 observation points. With a little bit of geometry, a little trigonometry, I can figure out how far away that mountain must be. Simple, elegant, and it works for small distances. Astronomers use this same trick to measure distances to nearby stars. It's called parallax. Imagine you hold your finger up in front of your nose and you close one eye, then open it and close the other. Your finger seems to jump back and forth, doesn't it? That's parallax. It's the apparent shift in position of an object when you view it from different locations. Astronomers do the same thing, but instead of using their 2 eyes, they use 2 opposite sides of Earth's orbit around the sun. 6 months apart, they observe a nearby star and measure how much it appears to shift against the background of distant stars. The shift is tiny, incredibly tiny, but it's measurable. And once you know that shift, once you know that angle, you can calculate the distance. But here's where it gets interesting. This method only works for relatively nearby stars. The farther away the star is, the smaller that angle becomes. You're measuring angles so small, they're almost impossible to detect. And here's the thing about measurements. Whenever you're measuring something that's very small, your uncertainty in that measurement doesn't get proportionally smaller. The errors stay about the same size. So if your angle measurement has an uncertainty of, let's say, 1/100th of a degree, that uncertainty doesn't shrink when you're looking at a star that's twice as far away. The star is twice as far, but your angle is half as big, which means your percentage error has doubled. Do you see the problem? And this is where NASA starts to have trouble telling you the complete story. Because beyond a certain distance, and we're still talking about relatively nearby stars just a few hundred light years away, this parallax method stops working well. The angles become so small that the errors become huge. So astronomers invented a new rung on what they call the cosmic distance ladder. Now let me explain this ladder because it's really the heart of why NASA can't give you a simple answer about distances in space. The cosmic distance ladder is a brilliant idea, but it's also fundamentally problematic. Let me explain it by making an analogy. Imagine you want to measure the height of a building, but you don't have a measuring tape that's long enough. So what you do is you get a small ladder and you measure the first 10 feet using that ladder. Good. You've got your baseline. Now you take a slightly taller ladder and you calibrate it against the first one. You can now measure 20 feet. Then you get a longer ladder, calibrate it against the second ladder, and now you can measure 40 feet. You keep stacking ladders on top of ladders, each one calibrated against the ones below it, until eventually you can reach the roof of the building. The problem is obvious when you think about it. Every time you add a new ladder, you're introducing new uncertainty. Maybe the second ladder isn't perfectly aligned with the first one. Maybe there's a tiny error in how you measured the first 10 feet. That error doesn't go away. It gets carried up to the second ladder. And then that combined error, the error from the first ladder plus the new error from the second ladder, gets carried up to the third ladder. By the time you're stacking 10 ladders on top of each other, the uncertainty at the top is not 10 times the original error. It's much, much worse than that. That's exactly what astronomers do when they measure distances in the universe. They build a cosmic distance ladder. The first rung is parallax, which works for nearby stars up to a few hundred light years. Once you get beyond that, parallax doesn't work anymore. The angles are too small. so they had to invent the next rung of the ladder. The next rung uses special stars called Cepheid variables. These are stars that pulse. They get brighter and then dimmer in a regular repeating cycle. Here's the clever part. The time it takes for these stars to complete one pulse is related to their actual brightness. If a Cepheid variable has a long period between pulses, it's actually very bright. If it has a short period, it's dimmer. This relationship was discovered by an astronomer named Henrietta Leavitt in 1912, and it's been incredibly useful. But here's the key. To use Cepheids as distance indicators, astronomers first had to calibrate them. They had to look at Cepheids that were close enough to measure with parallax. They measured those nearby Cepheids with parallax, determined their actual brightness, and then they confirmed that, yes, indeed, the period of pulsation correlates with the brightness. Now, they could use this relationship to measure distances to other galaxies. If they see a Cepheid variable in a distant galaxy, they measure the period of pulsation, they know what the actual brightness must be, and by comparing how bright it appears to be with how bright it actually is, they can calculate the distance. Sounds good, right? But do you see what just happened? The distance to those Cepheids in the distant galaxy depends entirely on the accuracy of the parallax measurements of the nearby Cepheids. If there's an uncertainty in those parallax measurements, if we've made an error in calibration, that error now applies to every single Cepheid-based distance measurement we make. We've carried the error up to the next rung of the ladder. And it doesn't stop there. Once astronomers know the distances to nearby galaxies using Cepheids, they can use those galaxies to calibrate the next rung of the ladder. This next rung uses something called type Ia supernovae. These are incredibly bright explosions that occur in binary star systems when material from one star falls onto the surface of a white dwarf, a dead stellar core. The explosion happens at roughly the same brightness every time, which makes these supernovae useful as standard candles. If you know how bright a supernova actually is, and you measure how bright it appears to be, you can calculate the distance. But to use supernovae as standard candles, you first need to calibrate them. And how do you do that? You use galaxies where you've already measured the distance using Cepheids. You measure supernovae in those galaxies. You know the distance. You measure the brightness. Now you can say, okay, supernovae are actually this bright. Now you can use that calibration to measure distances to supernovae and much more distant galaxies. Do you see the problem now? Each rung of the ladder depends on the one below it. An error at the bottom in the parallax measurements gets amplified as you go up. By the time you're measuring distances to galaxies billions of light years away, you're not just dealing with the original parallax error. You're dealing with accumulated errors from parallax, plus the error in calibrating Cepheids, plus the error in calibrating supernovae, plus errors introduced by cosmic dust, plus errors introduced by our incomplete understanding of how these stars actually behave. It's errors all the way up. And here's something that really bothers astronomers, something they don't often talk about publicly because it sounds uncomfortable. When different astronomers use different methods to measure the same cosmic distances, they don't always get the same answer, not even close sometimes. For example, there's something called the Hubble constant. It's the rate at which the universe is expanding. Different measurements of the Hubble constant disagree by about 10%. That might not sound like much, but in astronomy, that's huge. It suggests that somewhere in our cosmic distance ladder, there's a systematic error we haven't found yet. But where? Is it in parallax? Is it in Cepheids? Is it in supernovae? Nobody knows. And that's why NASA can't simply tell you the universe is expanding at exactly this speed. They have to hedge. They have to give you ranges. They have to say plus or minus. Let me tell you about another source of uncertainty that makes this even worse. When astronomers measure the brightness of distant stars and galaxies, they're not measuring light in a vacuum. The light has to travel through space, and space isn't empty. There's dust, there's gas, there's all kinds of material floating around in interstellar space. This material absorbs light. It's called extinction. A distant galaxy might look much dimmer than it actually is because of all this dust between us and it. Now, astronomers have ways of trying to correct for extinction. They can look at the color of the light. Dust tends to absorb blue light more than red light, which is why distant galaxies look redder than they should. But here's the thing. Different kinds of dust absorb light differently. The dust near one star might be different from the dust near another star. So the correction you apply depends on assumptions you're making about what the dust is like. And those assumptions might be wrong. Add another layer of uncertainty. And then there's gravitational lensing. Light from distant galaxies travels through space in straight lines usually, but when that light passes near something very massive, like a galaxy cluster, the gravity of that massive object bends the light, like a lens-bending light. The light takes a curved path instead of a straight path. Sometimes this causes a distant galaxy to appear magnified. Sometimes it causes it to be dimmed. And sometimes light from the same galaxy takes multiple paths around the massive object, so you see multiple images of the same galaxy. Now, when you measure the brightness of that galaxy, you have no idea if you're measuring it magnified or dimmed or what. That introduces uncertainty. Now, I want you to understand something important. I'm not saying the NASA scientists are bad at what they do. I'm not saying they're incompetent. Actually, they're remarkably competent. They've built these incredible space telescopes. They've sent spacecraft throughout the solar system. They've made measurements of incredible precision. The Gaia Space Telescope, for example, can measure the parallax of a star so precisely that if you put Gaia on top of Buckingham Palace, it could measure the width of a human hair on top of the Empire State Building, 5,000 kilometers away. That's an incredible level of precision. But here's the thing, even with that level of precision in our measurements, the fundamental problem remains. We still can't avoid the cosmic distance ladder. We still can't avoid carrying errors up from one rung to the next. The universe is just too big, and the limitations of physics are just too constraining, and there's no way around it. And there's one more thing that makes this problem worse, something that really gets to the heart of why NASA can't tell you the simple truth. As you go farther and farther away from Earth, as you're trying to measure distances to more and more distant galaxies, you eventually get to distances so great that even the supernova method doesn't work well anymore. The supernova becomes so faint that even our best telescopes can barely see them. So astronomers invented yet another rung of the ladder. For the most distant objects, astronomers use redshift. When a galaxy is moving away from us, and all distant galaxies are because the universe is expanding, the light from that galaxy gets stretched out. The wavelengths get longer, the light appears redder. This is called the cosmological redshift. The amount of redshift is directly related to how fast the galaxy is moving away from us. And according to Hubble's law, the speed at which a galaxy is moving away is proportional to its distance. So all you have to do is measure the redshift and you can calculate the distance, right? Wrong. Because to use Hubble's law, you need to know the Hubble constant. What is the Hubble constant? It's the proportionality constant that relates distance to the speed of recession. And how do you measure it? You measure distances to nearby galaxies using the rungs of the cosmic distance ladder that you've already built. You measure their redshifts, and then you fit a line through the data to find the constant. But if your distances to nearby galaxies are uncertain, and they are, because of all those errors accumulated up the ladder, then your measurement of the Hubble constant is also uncertain. And if the Hubble constant is uncertain, then all of your distance measurements for the most distant objects in the universe are also uncertain, because you're calculating them based on that constant. This is why different teams of astronomers, using slightly different methods or slightly different data, get different values for the Hubble constant. And this is why, if you look at NASA's official statements about distances in the universe, you'll see them hedged with careful language. The distance to this galaxy is approximately this, with an uncertainty of about this much. They're not trying to be cagey. They're being honest about the limitations of what we can know. There's a concept in science called systematic error, and I want to explain it because it's crucial to understanding this problem. There are two kinds of errors in measurement. Random errors are things that happen by chance. You measure something, and sometimes your measurement is a little too high, sometimes it's a little too low. If you make lots of measurements, these random errors average out. You can reduce random errors by taking more measurements. But systematic errors are different. A systematic error is an error that always goes in the same direction. It's built into your method. For example, if your ruler is slightly too short, then every measurement you make with it will be too long. All of your measurements will be off by the same amount. You can't fix that by taking more measurements because every measurement will have the same error in the same direction. Now here's the frightening thing about the cosmic distance ladder. We can't even see some of our systematic errors. We measure distances using parallax. We use those distances to calibrate Cepheids. We use Cepheids to calibrate supernovae. We use supernovae to calibrate redshift. At each step, if there's a systematic error in the method, that error gets carried forward and magnified. And we might not know there's an error until someone tries a completely independent method and gets a different answer. This has actually happened. There was a famous case in the history of astronomy where two different groups of astronomers were measuring the Hubble constant, trying to determine the expansion rate of the universe. One group, using one method, got one value. Another group, using different methods, got a different value. It was a big crisis in astronomy. These two measurements disagreed by almost 50%. How could they possibly both be right? Well, one of them wasn't. And it took many years of careful work to figure out which one had the error and where that error came from. I'll tell you what I find fascinating about all this. The problem isn't that NASA scientists are dumb or incompetent. The problem is more fundamental. It's about the nature of the universe and the nature of measurement itself. The universe is big, really big, too big to walk across with a measuring tape. We have to use indirect methods, and every indirect method has limitations. Every method works over only a certain range of distances. And when you combine methods to extend beyond that range, you accumulate errors. It's like a game of telephone. You whisper a message to the first person and they pass it to the second person who passes it to the third person and so on. By the time the message reaches the last person, it's completely different from the original. That's essentially what happens with the cosmic distance ladder. The original parallax measurements made with such incredible precision by telescopes like Gaia are like that first whisper. But by the time the information has been passed through 5 or 6 different rungs of the ladder, combined with calibrations and corrections for dust and gravitational lensing and assumptions about stellar evolution, the message has changed. You've lost fidelity. Now you might ask, well, why don't astronomers just wait until the methods improve? Why don't they get more precise measurements? And they are doing that. The Gaia telescope is measuring the parallax of over 1 billion stars with unprecedented precision. The Hubble Space Telescope has been measuring Cepheid variables in nearby galaxies for decades. The James Webb Space Telescope, the newest and most powerful space telescope we have, is making observations that might help us calibrate the cosmic distance ladder more accurately. But here's the thing. Even as we make these measurements more precise, we're discovering that the errors we thought we'd eliminated are still there. We're discovering new sources of systematic error we hadn't thought about. For example, it turns out that the brightness of type Ia supernovae isn't quite as constant as we thought. They vary a bit depending on the age of the stellar system and the composition of the companion star. This means the calibration we did was slightly off. That means our measurements of distances to even more distant galaxies are slightly off. This is the eternal problem of science. Each time you improve your measurement, you discover that you were wrong before, but in ways that are much more subtle and interesting than you thought. This is what NASA is dealing with. They're not lying to you when they tell you how far things are. They're just not telling you the whole complicated, messy truth, because the whole truth is that they don't know as precisely as they'd like to. Let me tell you a concrete example. There was a crisis in cosmology a few years ago. NASA scientists, using the cosmic distance ladder to measure the Hubble constant, got a value of about 73 kilometers per second per megaparsec. That means for every megaparsec of distance, about 3 million light years, the universe is expanding at an additional speed of 73 kilometers per second. But observations of the cosmic microwave background, the light left over from the Big Bang, suggested the Hubble constant should be about 67 kilometers per second per megaparsec. That's about a 10% difference. And that difference is statistically significant. It's not a measurement error. It's a real discrepancy. Which measurement is right? Both sets of scientists are competent. Both have measured carefully. Both have checked their work. But they get different answers. This is called the Hubble Tension, and nobody knows how to resolve it. Some cosmologists think there might be a systematic error in the cosmic distance ladder. Others think there might be something wrong with our understanding of the cosmic microwave background. Some wonder if there's new physics we haven't discovered yet. But the point is, NASA scientists can't just tell you the Hubble constant with certainty because they're genuinely uncertain. They're not sure which measurement is more accurate. This is why NASA hedges its bets. When they publish official values, they give you a range. The Hubble constant is between this and that. They're being appropriately honest about the uncertainty. Now here's something interesting to think about. Why do you think we even care about measuring distances in space? What difference does it make? Well, it matters for science. It matters for understanding our place in the universe. If the Hubble constant is 73, then the universe is a certain age. If it's 67, the universe is a different age. That's not a small thing. The age of the universe matters for understanding how stars formed, how galaxies formed, how the universe has evolved. Get the distance measurements wrong and your entire picture of the universe's history is wrong. But here's what I really want you to understand. The fact that we can't measure cosmic distances with perfect precision doesn't mean our measurements are meaningless. The cosmic distance ladder, with all its imperfections, has taught us tremendous things about the universe. We know the universe is expanding. We know it's billions of light years across. We know distant galaxies are billions of years old. We have a detailed map of the universe's structure. We understand dark energy and dark matter. We've figured out the universe is made mostly of stuff we don't understand. None of that would be possible without the cosmic distance ladder, even with all its limitations. What NASA is struggling with, what they can't simply tell you, is that we're at the edge of what's currently measurable. We've measured what we can measure with our available tools and methods. We've pushed those methods about as far as they can go. To know more, to measure more precisely, we need either new telescopes or new methods or a deeper understanding of astrophysics. We're not there yet. So NASA tells you what they know, but with appropriate caveats and uncertainties. And that's actually a sign of good science. If NASA just confidently told you the universe is exactly this big and everything in it is exactly this far away, I'd be suspicious. Because we live in a complicated universe measured with imperfect tools by scientists trying their best to understand something bigger than themselves. The uncertainty isn't a failure. It's evidence that we're pushing at the boundaries of human knowledge. So that's why NASA can't tell you the simple truth about space distances. It's not because they don't know. It's because the truth is complicated. It's because measurements have errors. It's because the cosmic distance ladder is a beautiful but flawed instrument. It's because the universe is bigger and stranger than we can fully comprehend. But the fact that we can measure distances to the edge of the observable universe at all, the fact that we can take light that's been traveling through space for billions of years and use it to figure out how far away it came from, that's pretty remarkable. And the fact that we acknowledge our uncertainties, that we're honest about the limitations of our methods, that we keep working to improve our measurements and catch our mistakes, that's the best thing about science. So when NASA tells you a distance, and they give you a range, and they talk about uncertainties and margins of error, don't think of that as a cop-out. Think of it as honesty. Think of it as evidence that they're taking their measurements seriously, that they understand the limitations of their instruments and their methods, and that they're trying to tell you the truth, the whole truth, even when the whole truth is messy and complicated and doesn't fit neatly into a sound bite. The truth about space distances is this: we're measuring an infinitely vast universe with finite tools. We're doing better all the time, but we've got a ways to go, and that's okay. That's how science works.